Have you ever pondered over the accuracy of the dates assigned to ancient fossils? Let's delve into an intriguing aspect of paleontology that holds the potential to disrupt our comprehension of prehistoric chronology: the Fenton reaction. This fascinating chemical process takes place within the very fabric of fossil bones and teeth, a silent dance of molecules unfolding over eons. The Fenton reaction is a complex ballet of hydrogen peroxide and iron ions. When these two elements encounter each other within a fossil, they engage in an intricate chemical exchange, producing hydroxyl radicals. These radicals, while minuscule, have the power to damage the organic material within fossils, a consequence that fuels a fiery controversy in the field of paleontology. The crux of the contention lies in the realm of radiometric dating, the method scientists use to determine the age of fossils. This technique hinges on the radioactive decay of certain isotopes, a process that occurs at a known rate. By calculating the ratio of the parent isotope to its decayed daughter isotope, scientists can deduce the age of the rock or fossil. However, herein lies the rub. The Fenton reaction, through its production of hydroxyl radicals and breakdown of organic material, can potentially interfere with radiometric dating. This interference could result in the loss of uranium and potassium isotopes, leading to an underestimation of the fossil's age. Furthermore, the damage caused by hydroxyl radicals can make it difficult to extract DNA from fossils for analysis, an essential process for studying the evolution of ancient organisms. Yet it would be a misstep to paint the Fenton reaction as a villain in this narrative. Despite the potential implications, research suggests that the Fenton reaction's effects on radiometric dating are minimal. This reaction is relatively slow and unlikely to have inflicted significant damage to most fossils. Moreover, scientists have devised methods to mitigate the Fenton reaction's impact, such as treating fossils with antioxidants. However, the Fenton reaction is not a villain in the story of paleontology, but rather an enigma that continues to puzzle scientists. To unravel this mystery, we must first delve into the heart of the Fenton reaction. This captivating chemical reaction is named after Henry John Horstman Fenton, a British chemist who first described it in 1894. In essence, the Fenton reaction is a biochemical process where hydrogen peroxide, a common substance, interacts with iron ions, often present in fossilized organic material. Imagine a dance of chemical entities where hydrogen peroxide, known in chemical parlance as H2O2, and iron, symbolized as Fe, take center stage. As they interact, they produce what are known as hydroxyl radicals, represented by OEHI. These radicals may sound benign, but they are anything but. They are extremely reactive and can wreak havoc on the organic material within fossils. These organic materials, which include DNA and proteins, hold valuable information about the life forms they once belonged to. When hydroxyl radicals attack these substances, they may degrade or even destroy them entirely. The resulting damage can be likened to ripping pages from a book, leaving the story incomplete and, in this context, potentially skewing the results of radiometric dating. Now let's venture into the realm of radiometric dating, a method used by scientists to determine the age of rocks and fossils. This technique is based on the predictability of radioactive decay, where isotopes of certain elements break down over time at a steady known rate. The two most commonly used techniques for fossils are uranium-lead and potassium-argon dating. These methods rely on the predictable decay of uranium and potassium isotopes. Over time, these parent isotopes decay to form daughter isotopes, and the ratio between the two can be used to calculate the age of the rock or fossil. It's like reading the rings of a tree, but on a much grander geological timescale. But here's where the Fenton reaction throws a wrench into the works. First, by breaking down the organic material in fossils, it can lead to the loss of uranium and potassium. This can result in an underestimate of the fossil's age, like accidentally skipping a few chapters in our geologic history book. Second, the generation of hydroxyl radicals can damage the DNA in fossils. This can make it difficult to extract DNA for analysis, limiting our ability to study the evolution of ancient organisms, akin to losing valuable clues to the past. Despite this potential for chaos, the Fenton reaction is not a villain in the story of paleontology. It's a natural process, part of the complex world of chemical reactions that occur in our environment. And while it can pose challenges, it also underscores the importance of understanding and accounting for all variables in our scientific exploration. We've delved into the intricacies of this chemical reaction, its potential effects on radiometric dating, and the ensuing controversy. Despite the challenges it may pose, we've also seen how paleontologists continue to navigate these complexities, ensuring the accuracy of our evolutionary history. Remember, every sip of science is a step towards understanding our world. If you enjoyed this journey, don't forget to like this video and subscribe to the Sci Sips channel for more scientific adventures.